Hello everyone and welcome to this optional walkthrough on using local open source large language models with Ollama. And so in our main lab, we use the cloud-based Gemini API, which is powerful and convenient. But what if you want more control, privacy, or just want to experiment without worrying about API limits? That's where running models on your own machine comes in. So this notebook is just for exploration and isn't worth any points, but it's a great way to deepen your understanding. So let's get started. So first up, the data preparation is exactly the same as in our main lab notebook. So we load our SEMable emotion dataset and get it ready for use. And so after this, um, okay, so then we can start in here. Just make sure that to have Ollama running in the background in order for the notebook to run correctly. Remember, I mean, I'm gonna be explaining that everything here by running it locally in my computer. But then you also see from the environment setup that we also have the notebooks in Kaggle and in Colab. So, but you'll be able to run them in the same way if you just run the first cells in those notebooks. Okay, after Ollama is in the background in the cloud, then you'll be able to run everything in the same way. Okay, so if you would like to check out on a tutorial on Ollama, you can also check this video, additional video here. And so let's see how basic prompting works with Ollama. So the code looks a bit different from the Gemini API, but the concept is the same. We use the Ollama.chat function, specify the model we want to use. Here, a small Gemma model is gonna be is being used here, the geometry, the 270 million version, and we pass it into our prompt, and then uh, we put the message, right? We put the role is a user message, and the content is what is data mining, elaborate on related topics. So we want it in Markdown format, and then we can just print it in this way. And the message, the content, and this is what we have, the raw markdown. And then we can also visualize it nicely in this way with the markdown command um, function. And this is what we have. This is very easy. So in this notebook, we don't have like a centralized function to call Ollama, but so we will be just calling it directly with their own format, right? With their own just directly with the Ollama chat thing. So right now we're gonna be checking out the structure output. So with the Gemini API, we use a special schema parameter, right? So with Ollama, the process is very similar, but we pass our Pydantic schema into the format parameter in the Ollama chat function. So you see here we have in this case this topics list, and we have a list of topics, and each topic has topic name, subsections, list of subsections, and the subsections contains a subtitle, a sub-explanation. So we do need this like Pydantic person to be passed down into the model. With Gemini, we could just pass down this list topic um, part, but in this case with Ollama, we do need like to wrap it up into this like more top-down, top-up version of like the schema, because we need to pass down this model JSON schema that we obtain from Pydantic. So just be sure to do that. There's a slight difference there. And so yeah, we also give the model a clear system prompt of what we want. And like we described that we need everything in a JSON schema. So it's important to note that smaller local models might struggle with complex schemas. So you may need to use a more powerful model for reliable structure output. And Okay, so once this is done, if you check out the response, so here, okay, so we can like validate that everything is correctly, like parsing the content. So this is how we do it. We use the Pydantic function model validate JSON. So we just validate the content as everything correctly. We can print the topics. Is what we have. Topics equal the list of topics, and then we can just dump everything to just check out this um, uh, the dictionary. So you see it's a type dictionary, and we can check out the topics names. You see machine learning, data centers. Um, you see here like the subtitles, what is the machine learning and everything, and all the subtitles inside the response, and we can also structure like everything in this way inside the like just in the print, right? It's just topic, subsection, explanation, just everything like tabulated, and yeah, so this is already very similar with the Gemini, right? Now with the multimodal, right? Text plus images, um, is that we can also there's also models that are support like vision understanding, right? Like we explained in the environment setup, the Gemma 3 4 billion model. So we can just describe images also with this model, right? So it's we can do like very like simple multimodal prompting with Ollama. So it's in the Ollama.chat function alongside the text prompt. And here we just add these images parameters that you see here and provide a path to our image file. So here we're using, like I said, our model, Gemma 3 4 billion parameter that has vision capabilities, and we can describe the images of the dog and the cat. So so just be aware, this is just a direct implementation with the function logic. Okay. Um, we can see here it's a Shiba Inu. Just describing this, right? And then the cat, just description seems very accurate. Okay, and then so next is tool calling, and this is where we just give the model the ability to use external functions, and like we already saw in the bonus section with the Gemini, right? So it's the process is very similar to Gemini. So we define our Python function, again, the simple math function, and we create the declaration. So be aware that the declaration part, the like a structure is not exactly the same with the Gemini version. So so for example, this it includes this type function on the top. So in the Gemini part, it starts from this section to like for the whole declaration. So just be aware of that. There's this difference, and and so just we describe again what the function, the tool does, and everything. And we are using Llama 3.21 billion parameter because um, this model supports this tool calling. So not all models in Ollama and the Ollama like catalog support it. So you need to check it. You can filter through like in their catalog for the ones that can do that. So in this case, this one can works for that. So so yeah, so it's we we use this Ollama chat again. We specify the model, the messages, and then we also pass down the tools, the declaration, and then here we can see like the output. It outputs the tool call and the name of the tool and the arguments, the same way as in Gemini. And we can see the arguments as well, the first number, second number, and the operation that's needed to do. In here, I just ask for 5 plus 10. And then in here, like in the, we already saw in the Gemini part, it just put in the dictionary with all of our functions or tools that we're gonna be calling. And then in here, we are just um, executing the like the function call, pass down the arguments, we obtain the result. The output is 15, and then we are just like sending again the like just concluding right with our Ollama model, just passing down the output and just give an answer to the user. And so it's okay, calculate a result. The result of the calculation is 5 plus 10 is 15, and yeah, just an explanation here. Okay, so this is the logic with tool calling. And now for information extraction and grounding, we're using Langstride again. So um, so the only change here is also that we're gonna be that the library also supports to use Ollama. So we're just changing that to use Ollama in the backend and not Gemini. And so we're gonna be loading the same document example that we had, the reviews for Interstellar. We loaded like we already saw for phase two, the main notebook. We have the same, I mean the a similar prompt, but in this case I didn't put that much detail into it because it was too complicated for the model to perfectly understand. So I just trim it down to a more like simpler explanation. Because like I said again, these are open source models, but are very very smaller models compared to the proprietary models of that like Google has, right? The Gemini ones. So I just simplified this prompt and the examples, and and then in here the only changes was that we are uh, we are like the max character buffer, the limit was brought down to 400 characters, and then that we are like using the server that where Ollama is running in the background, that is usually in this port, 11,434. Um, so usually it will be like served at this port, so it's like the default one. So if you are like running maybe like a very specialized servers where maybe you need to use another port, then you change this number, right? So so in this way, like this Langstruct pipeline can work in the same in the same as in Gemini. So we obtain these extractions again, opinion statements, and the audience impact, and so we can see in here the same like visualization. We can just move around and see what our model is outputting. The one we are using here is Gemma 3 4 billion parameters. So so I see that with this model we can obtain like sufficiently enough like good quality extractions. With like smaller ones, I was having some problems. So be aware of that, right? That you need to check how the model output is doing. So so yeah, so I see that maybe starting with 4 billion, it's better, more like stable. Um, so that will be it for information extraction. And now we're gonna start with how to implement a retrieval augmented generation with Ollama. So we're gonna just build it with the local models, right? So we are using the LangChain library again, but we are swapping out the Gemini components for Ollama compatible ones. And so for embeddings, we use Ollama embeddings in here, and so we are just selecting or embedding Gemma model here, and for generation we are calling the Gemma 3 270 million parameter model one that we downloaded. So like the rest of the pipeline is the same. We have the URL, we have the retriever, and then we have the question that we pass down to a RAG pipeline, and then we obtain these results. We are using a different URL here. So you're seeing here that we are asking about what is explained about the new architectures that have emerged in the because it's about like large language models, right? The topic in IBM URL. So it's talking about Mamba models and diffusion models that just for like a little like context. Mainly LLMs are based on transformer architecture, right? But then right now there are like some incoming new architectures that are these ones, the Mamba models and these diffusion ones, and that it seems like they are promising and that can maybe it will be like the new mainstream. We don't know yet, but are showing like good results, like comparable to the transformer architecture based ones. Like so anyhow, like we see inside it here that indeed that was like the correct answer. It's calling about is talking about Mamba models and diffusion LLMs inside the URL, and it was picked up in the context that was passed down for the RAG pipeline. So it seems it's correct, and so yeah, so that was the pipeline for RAG. Now we're gonna check the LLM embeddings, how to generate them locally with Ollama. So okay, so let's generate them. Okay, and we're gonna do them for the entire data set, and we're gonna use them to train the classifier, like we mentioned for in the main notebook explanation. That in this case, because we are running it locally and we don't have any like rate limits problems, we can basically obtain the embeddings for everything in the data set. So, and we can do this. Before we couldn't, right, in Gemini. So we're gonna take advantage of this for this Ollama part. So 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 of course we're gonna be generating the embeddings for all the training and the test data. So not sample, right? So just gonna do this. So we have this function generate embeddings, and we're using again embedding Gemma model, and we are gonna be passing down this the text column that from the data frame, and so we obtain them in here for training and the test, and it will look something like this. We have the embeddings now for all the rows, and then we can visualize it in UMAP again in like 2D, and it will look something like this. Is better visualization, right? It has the same like data inside each point. You see the emotion label, the text, and intensity. So in the same way, we see that even with all the data, there's not really clear the separation in 2D. So uh, it's just what we have. Like, there's no so it's just because of the emotions, right? They are not so discrete, right? So to get reflected in this dimension. So it's this is what we have now. With embeddings for all our data, we can now train some classic machine learning models. We first train a k-nearest neighbors (KNN) classifier on the embeddings and get it. And you see that after just passing down the training, the x and y values, right? And training for 10 neighbors, we fit the model and we predict, and we see that the accuracy for the model was 61%. We have here the classification report. We see that from the F1 score that the best the best like label that was classified was a fear label. So, and the least one was a sadness label. So okay, so this is with KNN, and can plot here also the confusion matrix for this. And then we can also try to compare with try to apply the neural network to the embeddings and see what we can get. And so we pass it down to the model. So first we need to like encode the the labels into one hot encodings, and then you can see here like so the embedding size is 768, the one that embedding Gemma provides. And so output shape is 4 because we have 4 labels. So we build our neural network, and we can see that so after training with for 25 epochs and batch size 32, we see like testing accuracy of 65%. So we can see that it was better than KNN. And so here we can also just plot. So you see, I mean, it seems that in the same way as KNN, the best like predicted label was fear, and the worst predicted label was sadness. And but then overall it was better than KNN, right? So this is what we can get now that we have all our data. We could train this properly. And this is just some applications, right? What we can do. So this just demonstrates this practical workflow that using a powerful LLM to create rich feature representations, like the embeddings, and then feeding those features into traditional models for a classification task, right? That what we see here. Now, to end this with the few shot prompting classification, it's mostly the same as what we saw already before. And in our main phase 2 notebook, we have our labels, we have the schema. The only change is that we are like wrapping it up into another pydantic class for emotion, this label here. And we are using the Llama 34 billion parameter version for the model. And everything else, well, we just build the prompt, sample the few shots. We are just classifying with the LLM. We're using, like I said before, this model, and inputting here. And so we extract the emotion result in this way, just validating here, and then just dump and select the label key from the dictionary, and it contains our label options, right? Either anger, fear, joy, and sadness. And then we just basically append, like just collect everything, right, for all the 20 test examples per category, and just plot the confusion matrix and get the classification report. So in the same way, we have here the experiments for 0 shot, and for 1 shot, and for the 5 shot one. So this remains the same, and you can see at the very least the best accuracy that we got, like in this case, was actually the 5 shot version that got accuracy of 50%. And yeah, this 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 will be like all. That concludes our tour of Ollama and local LLMs. You have seen that you can perform any of the same advanced tasks from multimodal analysis to tool calling and drag right on your own machine, right? So while cloud APIs might offer more power and convenience, running models locally gives you unparalleled control, privacy, and freedom to experiment. So I hope this optional notebook has given you a taste of what's possible with open source models. So always thanks for watching, and yeah, just good luck on the rest of the class.